That countdown always reminds me of FIFA. Anybody here play FIFA? Nobody plays FIFA on the Xbox? Well, one of you guys is saying yes. Yeah. FIFA, yeah. Soccer. So whenever before you start your next match, it counts down. And it always reminds me of that. So just really quick, to remind you guys of what we did. If you were not here yesterday, the notes are online, like I said, or the video's online as well. So you can get it from there. But this was the idea. And I just want to remind you of what we've done so that when we do the stuff we're going to do right now, it doesn't seem like foreign, okay? So there was a job contracted to a metal shop, and they said, look, we want to make a planter for plants, okay? And we want you to create it out of a 15 by 25 inch metal sheet, okay? They wanted this to be constructed. So what we did is we said, okay, if we're going to construct a metal sheet into a planter, we got to cut out 4 congruent edges, right? And then we're going to fold it up, and we're going to weld everything together, and we're going to have it done. So the first part that they had us do was they said, okay, draw a sketch of what this is going to look like. So we drew a picture, right, a 25 by 15 inch metal sheet with squares on the edges, right? So we did that yesterday. And then they said, well, in a group, so we kind of decided we're just going to kind of work on it together. We're going to show what the volume was for specific measurements, like any measurements you wanted. But I just picked, you know, what if the square is like 1 by 1 or 2 by 2 inches or 3 by 3 inches or 4 by 4 inches, right? So I decided to pick 1, 2, 3, and 4 just to try to keep it easy, right? I didn't want to go like 15, 25 or anything like that. Let's just go with something small. So I said, all right, we're going to try picking x equals 1, 2, 3, and 4. But before we could actually figure out the volumes, we kind of realized, well, I can't do this unless I know what the volume is. So that's where question 3 came into play. So we said, well, what is the volume, right? We know volume was length times width times height. And with volume being length times width times height, I look at this right here and I say, okay, well, I know my height is x because that's the cut. So when it's cut and you move it up, that becomes a height, right? So the height is x. I knew that. Okay? That's my x value. But my length would be 25 minus 2 cuts, right? And those 2 cuts, they're x each. X and x. So it'd be 25 minus 2x. So we wrote 25 minus 2x for the length. And the width would be 15 minus 2 of those cuts. So minus 2x as well. So here's the 15 minus 2x. So we said that the volume for this box is this equation here. X times 15 minus 2x times 25 minus 2x. Once I got that, I came back up to 2 up here and put in 1, 2, 3, and 4 for my values. And we got these volumes. Okay, so we kind of calculated everything. I know I'm going kind of quick, but again, if you want to see this done step by step, watch the video. It's online. Okay, but after that, we went and we moved on, and they said, you know, describe how the volume changes based on the cuts. Well, the smaller the cut, the longer the shape was, right? It wasn't very tall. And if you guys remember, the shape was kind of like this tall with the 1 inch cut, and it was pretty wide. Okay. Kind of long and stuff, but then when we made the cut a lot larger, so when we cut like a 3 inch by 3 inch square on all the sides, it became like this real tiny box. It was really deep, right? It was kind of deep inside, but it was real small, right? It looked really small. So the larger the square, so if x is large, meaning the dimensions of that square, then it was taller but not longer, right? So we kind of saw that yesterday with cutting of the cardboard and stuff like that. Now, on page 5, which is where we kind of stopped, they said, okay, create a table with up to 13 inches of cuts. So 1 inch, 2 inch, 3 inch, etc. Right? And we went through, I labeled everything over here in red, right? I told you that the height was x, the width was 15 minus 2x, the length was 25 minus 2x. We did these 4 previously, right? 1, 2, 3, and 4. We did those in part 2. But we calculated all of this stuff, okay? And in calculating it, we found that every one of these things kept going down by 2 units every single time, right? And every single time for this one as well, it was going down by 2. And I asked you, like, do you guys know why it goes down by 2? And I told you about slope, right? mx plus b, right? mx plus b. So your slope is -2. That means it goes down twice for every 1 unit, right? 2 over 1, -2 over 1. So it goes minus 2, all the way there. So just something that I told you to kind of notice. It's kind of an interesting thing to see, because you kind of see how the math connects with other things that you've learned before. Because we're doing quadratics right now. We're doing cubics and stuff like that, but yet you still get lines kind of integrating themselves into the problem. But anyway, we went through this and we started calculating everything, and then we noticed that there was a certain point where the width became negative. And that's not possible. You can't measure negative distance. Okay, distance is only positive. So we said, okay, that doesn't make any sense. And in the problem, if I look up here, it says, draw a bold horizontal line through the table to separate the rows that create real boxes from those that are impossible. So there's that line that we said, like, okay, everything from here down doesn't make sense because we have negative measurements, right? Negative measurements doesn't make sense for our box. All right, so we did that. And then we answered these questions and we were done for the day. We said, is the volume of the function a function of the size of the cutout of x? In other words, does the volume change based on the size of the square that you cut out? Yes, we just saw that with all that information, right? It changes. Then they say, what are reasonable restrictions? And we talked about this, right? This was the last thing we did. We talked about it and we said, well, the reasonable restrictions would be from 0 to 7.5. And I told you, here's how you could figure it out. And I did the work for you guys. But we're actually going to talk a little bit more about that today once we're done with the graph, okay? Like, we're going to talk about, like, how would you have known it's 0 to 7.5? Because I know because of the fact that I've done this for so many years, right? So it's like, oh, easy. This is where you find it, right? But what if you didn't know? Like, where could you find this information out? So we're going to talk about that. But we found it from 0 to 7.5, okay? And then I showed you what it would look like if I cut it at 7.5, like the box basically almost disappears, right? So it wouldn't have been good. But this is where we're going to start today. So you guys should have your worksheet out with you. And what I'm going to do is I'm going to draw this graph, okay? So you can check your answers, okay? So we start off with 0, 0. Remember, x and y. The x is the height, y is your volume, okay? So for 0 height, you get 0 volume. For 1 height, you get 299, okay? It's almost 300. So right about here. Now, it doesn't have to be perfect. Just kind of make it close, okay? For a height of 2, we get 462. So about here. A height of 3, we get 513. So right about there. And then for the next one is 476. So that's right about there. So right now I'm at the height of 5 at 375. So that's right here. Okay. Height of 5, 375. Height of 6, 234. So 234 would be somewhere around here. I'm just estimating, okay? And then height of 7 is 77. So let's see, 25 to 100. So somewhere around here. Okay? And then all of a sudden, we get negative volume. So I'm going to kind of move down a little bit. So for 8, I get negative 72. So 8, I get negative 72. And then a negative 189 for 9. So let's see, that's 50, 75. So negative 189 somewhere around here. And then negative 250 for 10. So there you go, negative 250. And at 11, I get negative 231. So somewhere around there. And then negative 108 for the next one. So negative 108 will be around here. And the last one is 143 at 13. So 13, 143 is going to be somewhere about there. And now I'm going to draw this. I'm going to connect the dots using a curve. Okay, I'm going to kind of do what I can, and then I'm going to scroll up a bit. Let me scroll up really quick, and then I'll zoom out, because then we got to talk about this. All right, so let me zoom out a little bit. Yeah.
So for this, like say on a test, would you suggest us to Since we stopped on our graph, our table graph,
Yeah.
with like a limited amount of like numbers, we don't do that error, right?
On a normal test, granted, you're not going to get something like this on a test, just so you know, because this is way too much work to do just to graph this, right? This took us like about 15 minutes yesterday of writing everything down. And that not only was it 15 minutes, but I had already done the work for you guys. I spent a bunch of time just calculating this stuff for you guys really quickly. So we try to kind of cut corners yesterday. But yeah, on a test, usually they'll give you a certain amount of numbers. 13 is crazy, but they might give you like 2 or 3, maybe 4 to try out. So anyway, this is what it should look like. So kind of make sure yours looks very similar to that. I had one student who just graphed up to here and then she stopped. And she's like, is it okay if I stopped right there? And I said, why do you think it's okay to do that? She says, well, because after that point, the volume becomes negative, and then all of this stuff doesn't matter because they're not real boxes. And I said, perfect. You didn't have to go all the way. You could have stopped only where the boxes were real. So she kind of understood that, kind of said like, oh, I can stop here. I don't need to do the rest. But if you did all of it, it's going to look like this. Okay, cubic function, right? Because it changes direction 2 times. Right? So if it changes direction twice, right, it's going up, down, that's one direction change, then down, up, that's another. So you always add 1, that tells you the power. So it's 3. This is a cubic function, okay? So with this in mind, let's look at question 8. What patterns, if any, do you notice on the table? Now, we did this yesterday. We just didn't get a chance to write it down. We said the length and width go down by 2 units when the height goes up by 1. Okay, that's something we notice. We also notice, if you pay close attention to it, that the volume is not only a positive number, it actually changes to negative as well, right? So I'm going to write that down really quick. I'm going to put volume is positive and negative. I'm just going to kind of do a short writing for it, okay? Just abbreviate it. So the volume goes positive and negative. Okay, that's something else we notice. Now here's the part that I told you we're going to kind of discuss. It says, what do the x-intercepts mean in the context of the cutout length at the volume of the box? So in other words, if you look at your graph, what do you think it means when the graph crosses the x-axis? Well, the domain. Remember how there was that problem that said, from where to where does this graph make any sense? Let me really quick find out what the question was, but it was right here. It says, what is a reasonable restriction of the domain? And we said 0 to 7.5, right? So when they say, what do the x-intercepts mean? It's the domain. This is where the box actually can occur. Now let me go back to the picture really quickly. What does that point look like? What is the measure of that point that I just drew right here? What's the x value? Let's see. 1, 2, 3, 4, 5, 6, 7 and a half about, right? And isn't that what we said the reasonable domain was? 0 to 7.5, right? There's another intercept here. That's about 12 and a half or so. But it doesn't really matter because the boxes don't exist here, okay? But the x-intercepts tell you your domain, like what's important, okay? So in other words, for us, the only numbers that matter are from here to here. Those are the only x values that make sense. Everything else, you don't pay attention to. Okay? But that's our domain. So when they say, what do the x-intercept mean, bless you, those are the domain. Okay? How could you have found the x-intercepts just by looking at the equation from question 3? In other words, without looking at a graph, could you have figured out the answers of 0, 7.5, and 12.5? Okay, I'm telling you it's about 12.5. My graph's a little off, but it should be 12.5. You could, guys, you can do this, and you've been doing this. You just may not know that you've done it. But you know how we've done like factoring of quadratic equations, and then we would factor them and set them equal to 0 and solve? Right? We did that like no more than a month ago. Okay, we've been doing this. Well, that's the same thing you do here. You're going to get your volume formula, which is already factored, and you're just going to set each piece equal to 0. So you're going to say, all right, if x is equal to 0, 15 minus 2x equal to 0, 25 minus 2x equal to 0. If you solve all three of those, look what you get. This is x equals 0, duh, right? The other one is 7.5 is equal to x, and the other one is 12.5 equals to x. That's where this graph is supposed to cross the x-axis. So whenever they ask you, can you find the x-intercepts, all you do is you set your equation equal to 0 and get each piece, set it equal to 0 and solve. Okay? So they're saying, could you have done it without looking at a picture? Yeah, I could have. I just get the equation and set it equal to 0 and solve for each piece. Okay? Now they say estimate the maximum volume. What was the most volume? Look at your chart. What was the highest number? 513 cubic inches at x equal to what? What was the x value? Was it? I think someone said it. 3, right? 3 inches. That's where it happened. Estimate. Whenever they say the word estimate, that means that's probably the wrong answer. Okay? But it's a good thing that we wrote that. That's good. We did the right thing. But usually when they say estimate the max volume, the very next question is, okay, do you think that's right? Okay, and that's exactly what they say. Are you confident that you found the maximum? So most likely you're supposed to say no. And why? Because estimate is the same as saying guess. Right? It's the same like saying guess. What do you think the answer is? Oh, well, here it is. Now, might you be correct? Maybe. Chances are you're not. Okay, because you're guessing. Right? So this is what they're saying. Are you confident that you found the maximum? No. Okay? What tools might you use to verify the maximum? Well, this is a thing that we've been trying to tell you guys for a long time, using Desmos. So let me show you what this looks like. Okay, what your maximum is going to look like. And you're going to see that we're actually pretty close, but we're not right. Okay, so let's check this out really quick. So... all right, so I'm going to graph the function that we have, and I'm going to go to the highest point of that function, okay? So I think it's x times 15 minus 2x times 25 minus 2x. Now, I know this graph doesn't look much like what we have right now, but let me just move up to it, okay? So I'm going to move up. Whoops. I'm trying to zoom out, sorry. So still going, almost to the top. I know the top is somewhere at 500. So almost there. Almost there. All right. So here's our graph. Okay. Here's the top of the graph. Look at the x value. This is the actual highest point. Now look what it is. 3 point, but then 0.34. We said 3. That one's 3.034. So let me write that down, right? Write that down on your paper. When they say what is the actual one, you're going to put x is 3.034. And the actual volume is not 513 at the maximum. It's 513.051. That means that 513 actually isn't the highest. There's a little bit higher, okay? 51 thousandths of an inch, of a square inch higher, or cubic inch, sorry. It's not a lot, but it is the highest. So you're going to use Desmos for this, okay? So let me leave that right there. I'm going to come over here to 400 for a reason. So give me a second. All right, so let me go back to this right here. So let's write that down. What tools might I use to verify if this is truly the maximum? No, Desmos. I'm just going to put right here volume of 513.05. What was it? 51? Cubic inches. That's the max, and that happened at x equal to 3.034 inches. Okay, so that's where it happened. Okay, now Number 13 is a whole new problem, but it deals with everything we've done. Okay, so far what we've done is we see all these UCI lessons. This is what this is, these UCI lessons, these big old little project problems. Number one, the reason why UCI, the University of California of Irvine, wants you guys to get used to this is because all of your state tests, there's always that one task that you have to do, right? It's a task. It's not just like a little test, but it's like this 3-4 part problem that you got to kind of go little by little and build your information so you can get a right answer. Kind of like this. Okay, you build information, right? So now they're going to give us the task. Okay, so now that we know how to find our intercepts and stuff like this, and we already know how all our answers and everything like that, then they ask us the following. They say, we want a new planter box, okay? And a garden shop has asked you to design a rectangular box with a volume of 400 cubic inches, starting with the same dimensions. So in other words, they're saying, look, don't change the problem. We're still going to do a 15 by 25 inch metal sheet, but we just want it to hold 400 cubic inches. Okay, they're giving us a maximum amount, okay, 400. What are the two possible dimensions of planter boxes with a volume of 400 cubic inches? And why are there two different possible boxes? So let's look back at Desmos. Okay, let's look back at Desmos. They told me 400 is the maximum amount, right? So let me type in y equals 400. And check this out. Let me zoom in. I forget that I can't just move this. So here's the graph. Here's the red line is the graph that we had originally, the one that goes up and down and back up, right? And here's the limit of what they told us. They said it has to be 400. So I type in y equals 400. Okay? How many times do they intercept? Twice. So why are there two boxes? Because there's two intercepts. Write that down. When they say, why are there two different boxes? Because the line y equals 400 and the volume function intercept twice. Okay, the reason why there's two boxes is because the volume function and y equal to 400 intercept two times. You might want to write down the x values, okay? 1.525 is one of them, and 4.793 is the other one. Now that's your height, by the way, okay? Remember the x value was your height, and the y volume, notice, 400. That's your volume, right? Both of them have a 400. So 1.525 and 4.793. I'll write those out again, don't worry. So let me write that down really quick. So why are there two boxes? There are two boxes because y equal to 400 and v equal to x times 15 minus 2x times 25 minus 2x have two intercepts. Okay, and I'm just going to say x equal to 1.525 and the other one was 4.793?
Yes.
All right. And then they say, what are the two possible dimensions of the planter? Okay, so they want dimensions of the planter. Okay, so we have two sets. Because either it's going to have a height of 1.525 or it's going to have a height of 4.793. So we're going to calculate them. So I'm just going to write it right here. Dimensions. So length, width, and height. I already know one of the heights and the other one as well. Length, width, height, 4.793. I just got to find the lengths and widths, okay? Well, that's kind of easy because if you guys remember, look back at your chart, this chart right here with all of this information. I told you that our width is what? There's a formula I wrote under where it says width in inches. What's the formula? for the width? Say it out loud if you know it. 15 minus 2x. And what's the length? 25 minus 2x, right? And the height is x, right? So that's why I put the x values under height, because that's what we said. Height is x, right? So to figure out the height, I'm just gonna, or the length and the width, I'm just gonna use the calculator real quick. So let's see, 25 minus 2 times, let's do 1.525. That we're gonna do the first one, okay? So give me a second just so I can do this. So 25 minus, oh, I was getting stuff in the thousands. I'm like, why is it thousands? I put a comma instead of a period. So it's 23.95. And then if I do 15, so 15 minus 2 times 1.525, I get 11.95. So there you go. That's one box. The other box, let's use 4.793. I'm just plugging that into my little formulas of 15 and minus 2x and 25 minus 2x. So 4.973, that's 5.054 for the width, and the length is 15.054. And those are the two boxes that I can build. And these are all in inches, right? This is inch, 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 and inches. Okay? So we're done with the lesson. And then they have you guys do 2 homework problems. Now I'm only gonna make you do 1, just the very last page. But I do want you guys, if you'd like to try this, okay, look at the very next page. And then we're gonna talk about the homework that they're actually gonna give you. They mention a square base box. They say, with your experience of the previous problem, make an open top box from a 20-inch by 20-inch steel sheet, okay? So in other words, you have a square, and you're going to cut squares out. If this is 20, let's see if you guys can help me build a formula really quick, okay? And all these are x's. All right, because they mentioned that your square, you should cut out squares, right? Little squares, so they have to be the same thing. Then, what is my formula for this box? Okay, so remember, volume is length times width times height, right? And my height is what?
So it'll be 20 minus 2x.
20 minus 2x, okay, perfect. 20 minus 2x, what else?
20 minus 2x again.
All right, 20 minus 2x, and then? We're missing one thing. That's your volume. Or you could write 20 minus 2x squared times x. But that's our volume. Okay? What restrictions should be placed on the domain of this function? How do we figure out the restrictions? We just did it with the computer, right? We're going to graph this and look to see when it's going up and then back down, look for the x-intercepts. Figure out what the x-intercept, well, let the computer do it for you, right? Just touch it and see what it tells you. But it'll tell you what your restrictions are. I'll tell you right now, I'll give you the answer. That way you can try it on the computer and make sure you get it right. It's from 0 to 10. Okay? 0 to 10. That's your restriction. That's your answer for this. Put your answer right here, 0 to 10. But try it on your own using the computer. Make sure you get it right. Okay? Then they say graph the equation on the same axis as the original. Don't worry about it. Just make sure you know how to graph it on Desmos. Okay? Because that's where you're going to want to know how to do this. Even on the state test, guys, you're going to be allowed to use Desmos on your computers. So if you guys can get used to using Desmos, it's going to be easier for you to do stuff like this that's hard, because Desmos does all the work for you. You just got to know how to use it, right? Write similarities, cross out 17. Don't worry about it. And then 18 estimate the max volume. We're not going to estimate. If you're going to graph it on Desmos, should you be able to find the actual highest point? Yeah, you just click on the graph and click on the highest point. And there you go. Okay? Remember, when it gives you the answer in X, Y form, remember that the X is your height, the Y is your volume. So when they say what's the maximum volume, it's your Y value. Okay? So, let's go to the back page. Now, I told the other class, and I'm going to tell you guys the same thing. When you guys take your group test this Friday, okay, and I don't know what the groups are. I still haven't even bothered looking at how I'm going to organize. I think I may just make them do it randomly, okay? So, you guys better make sure one of those people in your group knows how to do this problem. And a student said, well, Mr. V, we don't know what our groups is. And I said, and that's why everybody must know how to do this problem, because you don't know who you're going to be put up with. Okay, but check out how I know there's going to be a problem like this on your quiz, like this long to do.
Test or quiz?
It's a quiz on Friday, yeah, group quiz. But check out the way the question is. Okay, it's not that hard. It looks difficult, but you guys have the opportunity to use Desmos and stuff like that. So check out the question. It says, use your knowledge from this activity. Well, don't worry, in the quiz it's going to give you a problem. Well, they say open box dimensions of 10 by 15. Notice the box is just a couple feet different, right? Instead of 15 by 25, it's 10 by 50. They say draw a picture. Well, we did that, right? We did that twice. Just draw a picture. Great. You guys hopefully can draw a picture, right? That's all we're looking for. 2, write the formula of it. Well, you just did it right now, and we did that before, right? We're just going to basically look at our picture and say, okay, this is the length, this is the width, times X, right? And that's going to be our formula. Multiply the factors to find the volume. Now, we never did this in this lesson, but you guys should be able, if I tell you X times, let's say, 10 minus 2X times 8 minus 2X, you guys by now are supposed to be able to, okay, distribute here, and then once you do that, distribute it again to get your polynomial. Okay, they're not saying that this is hard to do. They're just saying, hey, can you multiply it out for us, please? Okay, all right. Once you do that, graph it in Desmos. Great. What's the maximum? What letter do you look for, X or Y, for your volume maximum? Which letter is it? It's your Y, your height. Height. Where does it happen? What is the X value of the cutout? Well, that's just your X coordinate. Okay? It's not a hard question. It might look intimidating because it's like really long, right? But it's not a hard question to do. And with 4 people or so in your group, I'm guessing you guys will be just fine. Okay? But try to make sure you understand how to do these problems, because there for sure is one. I saw it. Okay? It's, I think, on the back side of the quiz. Okay? So for sure there's one. Okay? So make sure you guys understand how to do those type of things. So try this homework. This is your homework. The only homework you have to really do for this lesson. And if you don't understand how to do something, ask me tomorrow. But that's all we got to do.